Hello, pre-calculus students. This is Miss Robinson, and today we will be going through 4.4 vocab notes. Okay, so flip open to your 4.4 section, properties of rational functions, and open to your vocab. We are going to start with number 1, rational function. So a rational function is a function of the form r of x, rational function, equals p of x over q of x, where p and q, sorry about that, p and q are polynomial functions and q is not the zero polynomial. Okay, so obviously we can't divide by 0, so q cannot be the zero polynomial. Right. And then adding a little more to this definition, the domain of a rational function is the set of all real numbers except those for which the denominator q is 0. Okay, so if we think about this form here, r of x equals p of x over q of x, and we know that p of x and q of x are both polynomials, we know that the domain of any polynomial is all real numbers. So the domain of both p and q on their own should be all real numbers. However, we know that polynomials usually have some sort of zeros. We've seen that so far. So really the only problem we could possibly have here is when our denominator equals 0, that q of x. Otherwise, we have no problems with p of x, that can equal 0. And it's a polynomial, so we know we have no square roots or negative exponents to worry about. It's just this denominator we need to look out for when we're talking about domain. Okay, so right off the top of our heads, let's think of an example. So, rational function, let's think of two polynomials. So maybe we have 2x squared minus 4 over x minus 5. Very simple, right? I see right away that the polynomial 2x squared minus 4 is not going to give me any issues for my domain, right? 2x squared minus 4 has a domain of all real numbers. No problems there. However, when I divide by x minus 5, I know that x minus 5 has a 0, right? If I plug in 5 to x minus 5, I'm going to get 0. Then I'm going to be dividing by 0, and that causes a problem, right? So right away, I can see that my domain for this rational function is all real numbers except when x equals 5, except for that when that denominator equals 0, that q of x. Okay? Okay, well, so we've identified where we might possibly have some problems. Now, let's look at how this might affect our graphs. So whenever we have these sorts of problems with our graphs, or with our functions, they're going to show up in our graphs as either vertical or horizontal asymptotes. So let's go into a basic definition of both. So if we have r of x as a function, so we let r denote a function, then if as x approaches negative infinity or as x approaches positive infinity, the values of r of x approach some fixed number L, then the line y equals L is a horizontal asymptote of the graph of r. Okay, so if we look down here at examples A and B here, these are both horizontal asymptotes. So as we can see, my function r of x is approaching this value L, y equals L. However, it's never going to hit that y value of L. It's going to approach it continuously and never cross over the line on this side. So this is telling me that as my x approaches positive infinity, my r of x is never going to approach that L, that value L. However, on the other side, it could possibly cross this asymptote here, this horizontal asymptote. There is no saying that when it approaches negative infinity, the other side, it does not cross. Only in one direction, necessarily. It doesn't have to cross my horizontal asymptote, however, it may in another area. So see, it approaches here, it might cross over here. Now if I look at the reverse, so over here, I have as x approaches negative infinity, my r of x is getting very close to this y equals L value here. However, on this side, my graph can do anything else. It could cross. It could also follow along and approach L in this direction. So this asymptote is only telling me that in this direction, as x approaches this negative infinity, my r of x cannot equal L. And on this one, as my x approaches positive infinity, my r of x cannot equal this L. Okay, so that's the idea behind a horizontal asymptote. Okay, now a small definition for a vertical asymptote. So if we look back up here, if as x approaches some number c, the values, absolute value of r of x, approach positive infinity, then the line x equals c is a vertical asymptote of the graph of r. The graph of r never intersects a vertical asymptote. So if we look here at C and D, these are both examples of vertical asymptotes. Okay, so I have x equals c and x equals c here. So as I can see, as my graph approaches this c value for x, I cannot have any value for r of x. I cannot plug in x and get a value, an output value r of x. Cannot happen. Therefore, my graph here is approaching this value up towards infinity. Okay, so it's going to go very extremely close to the c value as it heads, as my y values approach infinity. However, it will never ever cross this line. Same thing here, even though it's approaching negative infinity for y, it is never going to touch this line x equals c. Means I can never have an output for this input c. Now these are usually where I'm having, or they are, where I have my difficulties with my domain. So these are the places where I'm not allowed to have domain values because I cannot plug in those values and have a defined value for y. So never ever can I cross a vertical asymptote. I cannot have these x values. That's why we have this asymptote. So up here, the graph of a function may intersect a horizontal asymptote or oblique. We'll talk about oblique in a minute. But never, never, ever, ever, ever a vertical asymptote. So if you have a vertical asymptote, you are not crossing that vertical asymptote. You are either approaching infinity on both sides, approaching infinity and negative infinity, or approaching negative infinity on both sides. Never ever crossing that vertical asymptote. Okay? Moving on, let's flip the page here. Okay. Now, before we discuss how we find a vertical asymptote, let's go over a definition of oblique asymptote, since we're going in that direction of oblique asymptotes. Okay. So, an oblique asymptote, very similar definition as before. So we would say if as x approaches negative infinity or as x approaches positive infinity, the value of a rational function r of x approaches a linear expression ax plus b, where a cannot equal 0, then the line y equals ax plus b, where a does not equal 0, is an oblique asymptote. Oh, I'm sorry, only one s there. Asymptote of r. Okay, so what's that saying is that instead of just having a y equals a number or an x equals a number, this time my function does not work on a linear scale. So anywhere that I have this linear equation, like in this example, I have an asymptote. So I cannot cross this line, at least as I approach it in this direction. I might cross it in another place, just like I might cross a horizontal asymptote. However, in one direction I am approaching this, and I am never crossing this oblique asymptote. So an oblique asymptote is much like a horizontal asymptote, except instead of just being y equals, it's an actual function. And we'll see how we get those actual functions a bit later. Okay, so now we've gone through a little and defined the different types of asymptotes we might have. Now we need to know how to find these asymptotes. So how do I know in which instances I have a certain asymptote or another? And how do I find them exactly? So if we go back up to number 3, we can locate vertical asymptotes very easy. We actually already know all of the information we need to know about finding vertical asymptotes. So if we have a rational function, r of x equals p of x over q of x, so the same form we defined earlier, and it is in lowest terms, so simplified as much as possible, then we will have a vertical asymptote x equals r if r is a real 0 of the denominator q. Okay, so any zeros of q will be a vertical asymptote. So that is, if x minus r is a factor of the denominator q of a rational function r of x equals p of x over q of x in lowest terms, simplified, then r will have the vertical asymptote x equals r. So essentially, we find all of those places where our domain has issues or our x's cannot be plugged in, those places on the denominator where q of x equals 0, and those define our asymptotes. Okay, so let's take an example. Say we have the rational function x minus 3 over x plus 2 times x plus 5. So I know, technically speaking, when I look at this function, that I'm going to have trouble in my domain with x not being able to equal -2 and x not being able to equal -5. So those are two issues I know I'm going to have, because -2, -5 are both zeros of that denominator there, that q of x that I'm dividing x minus 3 by. I know if I plug in -2, I get 0 on my denominator, causes an issue. If I plug in -5, I get 0 on my denominator, causes an issue. Okay. So those two issue places are going to give me my vertical asymptotes where I cannot have any y values. So I would say that my vertical asymptotes are at x equals my 0, -2, and x equals my 0, -5. Okay, and if we take our graphing calculators, clear out anything we have, and we graph this function. So I have x minus 3 divided by all of x plus 2 times x plus 5. Maybe make my window something standard like -10 to 10 and -10 to 10. And I graph it. I can see that at x equals 2, I cannot have any values, so I have an asymptote here at x equals 2. And then at x equals 5, again, I cannot have any values, so I have my asymptote here at x equals 5. Okay, so that's how we find vertical asymptotes. We identify where our denominator causes us issues, where our denominator equals 0, and this shows us where we cannot have any values, those vertical asymptotes. Vertical asymptotes are always of the form x equals, because it's always an x value that you cannot be having. Okay, so anywhere where x equals -2, I cannot have any y values. Anywhere where x equals -5, I cannot have any y values. Okay, so that's identifying vertical asymptotes. Let's move on to talk about horizontal and oblique asymptotes. Okay, so if we move lower, we see this information here about finding horizontal asymptotes or oblique asymptotes. Now, horizontal and oblique asymptotes, you either have one or the other. Okay. And I have a couple of cases for these ones. So, if a rational function r of x equals p of x over q of x is improper, now let's think about what improper means. So if we think about improper, when we think about an improper fraction, that means that the numerator is larger than the denominator, right? So maybe something like 7/4 is improper, right? In order to make it proper again, I need to make it a mixed fraction, right? So this would end up being 1 3/4. Okay. Same applies for rational functions. It's p of x over q of x. So instead of thinking about the numbers themselves, where 7 is greater than 4, we're going to look at the degrees of my polynomial functions. Okay, so we're looking at a rational function, r of x, where the p of x is a greater degree than the q of x. Greater than or equal to. Sorry. So if I have, say, an x cubed function over an x squared function, this is an improper rational function. Okay. So I see that my degree on my numerator is larger than my degree on my denominator, gives me an improper fraction. Okay. Also, if I had something that was maybe x squared plus 6 over x squared minus x plus 2, these degrees are equal, they are also considered an improper fraction. if I look at this, in order to decide what type of asymptote I have after I decide that I have an improper fraction, I need to divide. Always my first step, to divide. Okay? So if I take this first one up here that I created, x cubed plus 2x squared plus 1, and I divide it by x squared plus 4. So let's take x cubed plus 2x squared plus 1 and divide it by x squared plus 4. Now, sometimes we might be able to use synthetic division for this. Right now we need to be using long division because we have this squared binomial. Won't exactly work as cleanly with synthetic division, so we need to be able to also know how to use long division. So x squared goes into x cubed x times. Multiply x cubed plus 4x. Multiply by negative. Combine like terms. This is going to be 2x squared minus 4x plus 1. X squared goes into 2x squared. Positive 2 times. That gives me 2x squared plus 8. Subtract, and I am left with negative 4x minus 7 there. So this tells me that my polynomial function goes in x plus 2 times with the remainder of negative 4x minus 7 over x squared plus 4. Okay, so if I look at my options, my first option is if f of x equals b, a constant. We don't have that. My second option is if f of x equals ax plus b. So when we divided, the function that we got for this one was x plus 2, right? So our quotient after we divided was x plus 2, f of x. So that fits into this scenario right here. So this tells me that if f of x is some linear function ax plus b, which x plus 2 is, then the line y equals ax plus b is an oblique asymptote of the graph of R. So that tells me that for this polynomial function that I created up here, I have an oblique asymptote at x plus 2. So I would say oblique asymptote at y equals x plus 2. So the instant we see that we have an improper polynomial function, we need to divide. And that will tell us what instance we're looking at. So that was one instance. Let's look at another instance. So I also gave you this example earlier, right? X squared plus 6 over x squared minus x plus 2. Let's try to divide these. Okay. So if I take x squared plus 6 and I divide it by x squared minus x plus 2, let's see what happens. So x squared goes into x squared one time. I'm left with x squared minus x plus 2. And when I subtract all of this, my remainder is x plus 4. Okay. So I would write this as 1 remainder x plus 4 over x squared minus x plus 2. So this time, after I divided, I'm left with f of x equals 1, right? So we just had f of x equals 1 as our quotient. So if I read my number 1 option, if f of x equals b, a constant, which we have right now, we got 1, then the line y equals b is a horizontal asymptote of the graph of R. So if I get a constant after I divide my two functions, then I would say that I have a horizontal asymptote at y equals that constant. So for this one, I would say that I have a horizontal asymptote at y equals 1. My third option is if I get anything that is larger than a linear function. So if I divide and I get a quadratic, if I divide and I get anything larger than a linear function, then there are no horizontal or oblique asymptotes. My graph of R just approaches the graph of F, and I don't have any way to define those asymptotes. Okay, so really all I'm looking for is when I divide a function I get a constant. When I divide a function I get a linear equation. Or a linear function there. Okay? If I consider this idea for a moment, the only time that I can divide two functions and get a constant is if I have the same degree, right? Because those x's need to cancel each other out. So if my p of x and my q of x have the same degree, I'm going to have option 1. I'm going to end up with a constant. So when they divide, I'm just left with a number and a remainder. The only time that I could get a linear function is if I have one x left over, right? Some sort of function with just one x left over, which means that my degree of my denominator should be only 1 less than the degree of my numerator, right? Because that way, say when we divide x cubed by x squared, I'm left with 1x, right? So that means that the only time I'm going to get option 2, that oblique asymptote, is when my numerator is 1 degree larger than my denominator. And we can see that in the examples we chose. So in this example, we see that our degrees are both 2. They're the same. And when we solved for our asymptote, we got a horizontal asymptote at 1. And we got a remainder that was a constant. So that fits our 1 category. When we chose this other example here, the x cubed plus 2x squared plus 1 over x squared plus 4, we see that this degree is 1 larger than this degree, right? And when I solved that out, my remainder was x plus 2. So we said we had an oblique asymptote at y equals x plus 2. And that fits my second criteria. Okay. We do have another option. So what if my rational function is proper? Okay. So I would say if, move this over, if a rational function is proper, then the line y equals 0 is a horizontal asymptote of its graph. So if it's not improper, it is proper instead. The degree of my denominator is larger than the degree of my numerator for these two polynomial functions. Then I just have a horizontal asymptote at y equals 0. Okay, so that takes care of horizontal and oblique asymptotes. There's one other item that we should consider that affects what our graph should look like. Okay. Okay, so earlier when we defined locating a vertical asymptote, we kept saying that we needed our rational function in lowest terms, And we said that that was simplifying our rational function, right? Well, let's think about the cases where we would need to simplify. So whenever we would need to simplify a rational function, that means something's canceling out, right? So for instance, and just add this to the bottom or to the back of your page. If I had a function where I had a numerator and then something on the denominator like this, so x plus 2 over x plus 2 times x plus 5. And to make it more interesting, let's add an x to the numerator. Okay, so say I had a function like this. If I look at this, I know right away this is not simplest terms, right? Because obviously I have this x plus 2 in my numerator and my denominator that technically can divide each other out. They can cancel, right? So if I decide to cancel these, I'm just left with x over x plus 5. So technically that's not a vertical asymptote because that's only an asymptote if it's not in lowest terms. We need to make it in lowest terms. So for here, my only vertical asymptote would really be at x equals negative 5. Because technically, this negative 2, if I were to plug it in here, I would have negative 2 over 3, gives me a value, right? After I've simplified. However, if I look at my original rational function, I still can't plug in a negative 2, right? It still gives me a problem. If I plug in a negative 2, I'm still getting 0 times negative 2 plus 5. 0 times 3. It's still 0 on the denominator. It's still a problem even if I can cancel it out. So in my original, since it's still a problem in the original, I would call this a hole at x equals negative 2. This just means that technically I can't define x equals negative 2 in my original, because if I plug in x equals negative 2, I end up dividing by 0. But I kind of know where it's headed, because if I do simplify, I can see that it's going in the direction of negative 2 over 3. I know that technically it should head in that direction, it just can't ever touch that point, because in my original function it doesn't work that way. Whenever we see that this is happening, we call this a hole in our function. And if we define a hole, we would say that a hole in the graph is a place where the function is not defined but you could technically make the function continuous by defining it there. Okay. And what that just means is technically we can't plug in this negative 2. It's not defined there because we have this issue with dividing by 0. It's undefined when we divide by 0. However, we know where it's heading. We can technically say that it's going in that direction by defining the area around it. By saying it's going in this direction, just can't hit that specific spot. Okay. We also call these removable discontinuities. So we would say, so holes are removable discontinuities. And that just means that it's discontinuous in my original function, but technically I know where it's heading, so I can remove it so that I know the direction it's going. Okay. So when we graph these functions, technically my graph looks like it's going straight through this point. However, technically I have a hole defined at that point. Okay. And we'll see this in the graphing calculator. Okay, so if I take my graphing calculator and I plug in this equation that we just made up. Okay, so turn it on. Plug it in. So I have x plus 2 times x divided by all of x plus 2 times x plus 5. And I hit graph. Okay. So if I look at x equals -2, certainly looks like I have a value, right? Looks like it goes straight through that point. Doesn't seem to give me a problem. Let's look at our table values then. If I go here to -2, I have an error, right? So my graph technically removed that discontinuity when it was graphing it because it knew where it should go. It can go right through that point, around that point technically, because it knows where it should be heading at that point. However, in my original function, I still cannot define it at that point. So it still gives me an error just at that exact point. Okay. We can't really see these holes on our graphing calculator because of this idea of the removable discontinuity, because our graph doesn't have that exaggerated open hole like we make on our graphs that we hand make. However, we still need to know that these are there and that they exist. So the graphing calculator might not help you as much with this unless you can see it through a table, which sometimes it's not as easy to see. But we can look at our equations and know where things are canceling out and know where there should be a hole, even if it doesn't look like there is one on our calculator. Okay. Alright, so that is the end for the vocab. A lot of definitions to think about for these. Next, we'll be moving on to some examples, so prepare for that. Applying how to find all of these asymptotes of our graph. So lots of graphing in the future. Have a good night or day or whenever you're watching this. Thank you.